Okay, so we are going to continue where we left off yesterday, which is that we had got to the point where we were considering loop oriented optimizations. Now loops, otherwise known as for loops or while loops, are a very common occurrence in most signal processing algorithms, or in general in most compute intensive algorithms, because if you look at even high performance computing and the kind of problems involved over there, they are typically trying to do computations involving either vectors or matrices, and for the most part what you are trying to do is iterate over the one dimension of the matrix, multiply with something, accumulate, do some kind of computation, maybe do a matrix inversion, whatever it is, all of those, the kind of linear algebra problems or even the convolutions that you find in neural networks, all of them end up being some kind of matrix operations which ultimately get implemented as loops. So most of the time what you will find is that the highly compute intensive parts of signal processing as well as high performance computing algorithms end up being some kind of loops, for loops being the most common one. Okay. So it is worth spending some time trying to understand the kind of optimizations that can be done on those kind of loops. So without going, we will be going into detail on each one of these later. So before that I want to just talk about why loops are important, and in particular what is it that we are trying to optimize when we say that you are going to optimize the loop in a certain way. The biggest problem with a loop is the fact that there is a certain overhead associated with the loop itself, right. So when I write something like for I is equal to 0, I less than 100, I plus plus, and do sum is equal to sum plus I, right. The addition, the actual work being done inside the loop is very small, it is just one addition. But in order to do that, if we are considering software, then effectively what we will have is there will be one step which involves initializing the counter, which is a one time operation, that is okay, we do not want to count that as overhead. But on every run through the loop there will be an increment or decrement, in this case increment, we are going to add 1 to I, we are going to test a condition, is I less than 100 or not, and depending on that we will branch. Okay. So typically there, for every run through this loop you have to execute at least 4 instructions in software, right, whereas the actual work being done is only one instruction, add sum plus I. Okay. So it is very likely that if the main work being done inside the loop is relatively small, then the loop might become inefficient simply because of the overhead associated with it. Another thing that happens especially in software is the fact that if you are accessing memory locations, then how you access those memory locations becomes very important, because computers, processors nowadays especially, because of the fact that the DRAM, the external memory, is much slower than how the processor itself works, the processor then has to have some kind of a caching memory which can respond very fast but has a low capacity. So how does the cache work? How does it pull data into the cache so that the next access is done faster? That has a big effect on how loops work. Now from the hardware point of view, similar considerations, because what happens is, how do you implement a for loop in hardware? You will have some kind of a finite state machine and a counter. Okay. So there will be one step for initialization, one state for initialization, then as you are going through the loop there will be some kind of a conditional checking and some muxing. The muxing basically involves either the data that needs to be computed has to be sent to the appropriate compute unit, or we might have to switch state to get out of the loop and go to the next state. Okay. And if you have some kind of read and write operations inside the loop, there will be extra cycles required for doing that as well. Those also have to be accounted for. So in other words, you can see that there, because this is, so this goes back to our original thing, this is a common case. For loops are very common in most kinds of programs or most kinds of algorithms that you are trying to implement, whether it be hardware or software. So it is worth spending time understanding and trying to optimize them. So let us look at a few of the optimizations that can be done. One of them involves optimizations with regard to the induction variable. Now what is an induction variable? In this case I. Okay. In other words, the loop index is the one that we call the induction variable. This j is a computation that involves the induction variable, right, and if you look at what is happening over here, every time that I run through the for loop, j is equal to 4 into I plus 3 needs to be computed. Now 4 into I may not be a big deal, right, because after all I can do it by shifting or by multiplication, it does not really matter. The point is there are two computations involved, there is a multiplication and there is an addition. So almost certainly 2 clock cycles are going to get spent for doing that every time inside the loop. Okay. That is in addition to the loop overhead, which involves incrementing the counter, checking the condition, etc. Okay. And finally I have a function called y is equal to f of j. Now if it turns out, well, if it was just y is equal to f of j, then you might argue that there is some dead code elimination, etc. that could be done. I am not considering those kind of special cases. We will assume that y is something else, maybe it is a pointer, something is getting updated, or it is y of I which is getting updated in this way, right. So f of j, if it is not a very big computation, the j is equal to 4 into I plus 3 might itself become significant compared to the work. What can we do here? How can we reduce this work, not have that multiplication and addition inside the loop? Exactly, right. See, after all, what are you doing with I? I is running n times, it is going from 0 to n minus 1, but the only thing it is being used for is, one, to keep count of how many times you have gone through the loop, and secondly to compute some value of j which can then be used in order to do some work. Why not just straight away compute j? Okay. How do I do that? Let us look at when I is equal to 0, what is the value of j, right. So I would rewrite this for loop as something like this: for j is equal to, when I is 0, what should j be? 3. Okay. So I initialize it to 3. What is the condition I need to check for j less than 4 into n plus 3? Now keep in mind 4 into n plus 3 will be taken out by the compiler, constant folding. Okay. So it can be computed ahead of time, it need not be done inside the loop. Okay. So there is still only one initialization step. The problem is now it is not j plus plus. What should I do? J equal to j plus 4. Okay. And straight away I can have y is equal to f of j. Now what has this done? Anyway I had to do an increment on I and a comparison on I as part of the loop. Then I was computing j after that. Instead I straight away made j the induction variable and changed how much it gets incremented each time it goes through the loop. And as a result of that I have basically reduced a couple of cycles over there. Okay. Now the important point is this might look like a very minor optimization, right, but assume that this was a nested for loop, one for loop sitting inside another. The outer for loop runs 10,000 times, the inner for loop runs 10,000 times. The savings can be enormous. Okay. So do not underestimate the effect of getting small savings like this. Having said that, this is a classic case for what you need to be careful about premature optimization, right, because the savings that you get by doing something of this sort are relatively small. You should be looking to see what are the big improvements that you can get first, and this kind of thing usually either the compiler can take care of, or it is that final tweaking, the last stage to get that extra 5%, 10% performance. If you are declaring, so inside the for loop, so what you have is there is a for loop and I declare int a is equal to some constant, right, and then you are using a inside over here. Yes, the compiler can take it out, assuming that it can actually, what it will do is it will do an analysis of the loop and see whether the value of a is changing. If it is not, it can be moved outside the loop, right. So in fact one of the things that the compiler needs to do is, whenever you declare a variable in general, what happens in the C programming language is there has to be some memory space allocated for it. Okay. So some area of the memory, one location, if it is an int, then 132-bit location will be allocated for that variable. But if the compiler, when it does the analysis, it also does something called a lifetime analysis, right, and finds out, okay, when did the variable first come into existence, when is it last used. If that is basically within a small block like this, the compiler can do one additional optimization and say, I will not even declare a memory location for it, I will just keep it in a register, use it and dispose of it once I am out of the loop. Okay. So this, in other words, the fact that you have declared a variable over here does not guarantee that memory will be allocated for it, or that how will the compiler actually implement it finally in the software execution. If you want it to be a memory location, then you basically will have to do something like either declaring it as a global variable or something to ensure that memory gets allocated for it. Or of course, so one other thing which I forgot to mention yesterday but is important, what you will notice is that even in Vivado HLS and also generally speaking when you are writing C code, there are different compilation options that you can use. Okay. So, with the GCC compiler for example, if you give the default, it does not try to do much optimization. Okay. That is controlled by the -o flag which is given as one of the parameters to the GCC command. If you give -o0, essentially it does almost no optimizations. -o1 will do some very basic optimizations, -o2 will do more, significantly more optimizations, and -o3 will actually do fairly aggressive optimizations, including potentially things that can give you wrong results. Okay, because it makes certain assumptions on things like how many times a loop is going to run, what kind of whether you have done array bounds checking, whether you need to check whether you are reading outside of an array and so on, right. So, depending on the level of optimization that you tell the compiler to do, it will apply more and more of these techniques. By default, it will not. So, if you declare int a over here, it will actually create a memory location for it and do everything. But if it is trying to optimize, it will just make it a register. Alright. Loop fission and loop fusion are two related transforms that you can perform on loops, right. What does this mean? Essentially what this is saying is I have a loop which inside the loop I am doing two computations. Okay. A of I is equal to A of I plus 10 and B of I is equal to B of I into 7. Can you think of any reason why this might be a problem or why this is not the most efficient way of doing things? It relates to what I had mentioned about the fact that you have memory and you have cache, and then the CPU. Okay, so the CPU talks to memory through the cache. What does the cache memory do? Any time that you access one particular element, it pulls in that element first from main memory into cache and then from the cache to the CPU, and you do some computation. In this case, so what you are going to do is any time that you access A of 0, it will pull in the value A of 0, do some computation with it and write it back into A of 0, it goes back into the cache. When I access A of 1, A of 1 gets pulled in from memory, I do something with it and write it back into the cache. Now, there is something called locality of reference which people observed from large amounts of code that were written, which basically said that very often what happens is if I access location number 0, I am probably also going to access location 1, 2, 3, etc. Okay. So, the way that the cache works is usually that rather than reading in an individual memory location, I will read in a block and try and get this in here all at once. Okay. So, I will end up with a so called cache line which will contain A0, A1, A2 and A3, say. It might contain more, but at the very least it will probably contain at least some 4 elements or 8 elements, some small number like that. Okay. It does not make sense to pull in like 1k elements because very unlikely that you will be reading in that many at one shot and the overhead involved is too high. But what the cache is saying is, look, you are accessing A of 0, chances are you also want to access A of 1 after that. So, it pulls it in and does some computation with it. But the problem with this loop is I am accessing A of 0, in the next clock cycle I am hitting B of 0, not in the next step inside the same for loop, I am hitting B of 0. Okay. There is a possibility that both of them, right, so this is A, this is B, both end up clashing on the same cache line. Why does that happen? Because of the way caches are implemented. They do not always guarantee that different memory locations will go to different cache locations. You could have a cache conflict over here. If this happens, performance will be really terrible, because what will happen is I will access A of 0, it will pull the whole A line into cache. Then I access B of 0, it throws the entire A line out, pulls in B. Next iteration through the loop, again it has to throw B out and get A, then again throw A out, get B. Okay. Performance can become quite bad. This is of course an extreme case, but it is a possibility. what can you do? If you look at these two instructions, there is no dependency between them. So, I can easily write this as for A and another for loop that goes for B. Okay. Now, what happens? I do all the computations involving A first, optimal use of the cache, everything is perfect, it runs fast. Then I switch over to B, run all the computations involving B. Guaranteed that there are no cache conflicts over here. The problem is there is some extra overhead due to the for loops, right. So, it is a trade off. You need to sort of look at the actual implementation and decide whether or not this loop fission which was applied over here. Fission basically means splitting. The fission that we did over here, was it worthwhile? Okay. What about fusion? Now, look at this and this, they both relate to A of I. Okay. So, I could potentially have combined both of them, A of I equals something and C of I equals A of I something. This is good because at least A is being accessed twice. There is a slight possibility that C also ends up conflicting with the same cache location, but chances of that are less. If that happens, then you have other problems to deal with. At least you do not need to read in any other data, and more importantly, whatever you computed for A of I can immediately be reused out here. You might even be able to do some kind of constant folding, propagation, etc., and reduce some computation, not even have to do one extra read from memory. Okay. So, this is a case where loop fusion can be used. The advantages of fusion are two. One is, if there is a related data, then the cache, you do not need to have two hits to the memory, the cache will take care of it better. The second thing, of course, is you are reducing loop overhead, right, because every time you go through the loop, you have that increment, compare, jump, which can be shared across two sets of instructions. So, remember, all of these things are the cases where it is not always obvious that it is going to give you a benefit. So, the compiler has to take a call whether or not it is a good idea. In general, C compilers do not do this kind of fission fusion kind of transformations easily. They do it only when you have aggressive optimizations in place, right. This is one of those places where human intervention actually can make a big difference, right. So, this is one of the kind of things where even when you are writing the code, you can actually look at it and say, okay, if I split the loop, does it open up any options for me to do further optimizations later on.